Welcome students, in this video we will see the design of synchronous 3-bit up counter. We need to design the synchronous 3-bit up counter. The step 1 is determine the number of flip-flops needed. We need to determine how many flip-flops are needed to design the 3-bit up counter. So the 3-bit is available, so the 2 to the power 3 equal to 8, there are 8 states will be there. Capital N equal to 8 states. Because of 3-bit there are 8 combination, that is 0, 0, 0, 0, 0, 1, like that we have 8 states are available. In order to identify the number of flip-flop, the condition given is 2 to the power n greater than or equal to capital N. Capital N is the number of state, small n is the number of flip-flop required. Now we'll substitute 2 to the power 3. So in this problem it is clearly given 3-bit, so definitely we need 3 flip-flop, right? So it's directly we'll substitute n equal to 3. 2 to the power 3 greater than or equal to 8. So 2 to the power 8 is nothing but 8. 8 greater than or equal to 8. So this condition is satisfied. Greater than or equal is there. So both the side we have 8. So this condition is satisfied, so that 3 flip-flops are required, right? So in order to design 3-bit up counter, what we need? 3 flip-flop. From this condition we identify that 3 flip-flops are required. The next step, we need to identify which type of flip-flop we are going to use. Here we are going to use the JK flip-flop, right? We will use the any type of flip-flop we can use. Here in this problem we will decided to use the JK flip-flop. So the third step is we need to draw the state diagram. The state diagram is nothing but how the 3-bit up counter is going, right? So we decided there are 3 bits are available. So it start from 0, 0, 0, 0, 0, 1, 0, 1, 0. That is 8 combination. This is nothing but 8 combination. Because of 3-bit we are having 8 combination. In this problem it is given up counter. Up counter means it start from 0 and goes up to 111. Minimum to maximum. Up counter means from minimum it will go up to maximum. Minimum value is 0, 0, maximum value is 111, right? So this is nothing but state diagram, how the 3 bits are changing step by step. So from 0, 0, 0 it changed to 0, 0, 1. Then it will change to 0, 1, 0. Then 0, 1, 1. Then 1, 0, 0. Then 1, 0, 1. 1, 1, 0. Finally 1, 1, 1. Again it is goes to 0, 0. So it is a up counter. From minimum to maximum it is going. It's called a state diagram, right? Because of 3 variable, 3-bit we have 3 combination. There are 8 states are available. The state start from 0, 0 and it will go up to 1, 1, 1, right? Because of up counter. Now we are going to use the JK flip-flop. We will see what is the excitation table of the JK flip-flop. What is excitation table? From the output we can decide what is the input is required. It is just opposite of the truth table. Truth table is from input we can identify the output. Here from the output we are going to check what is the input is required. So this Qn is nothing but current state, present state. Qn plus 1 is next state, right? So present state, next state, J and K is the 2 inputs. For example, current state is 0 and next state also 0. Both are 0 mean what is the input required JK? J is 0, K may be 0 or 1. That is X. X refers 0 or 1. That means either 0 or 1, right? So for the current state and next state, both are 0, 0 mean the input what be required? J is 0, K is 0 or 1. Suppose if the current state is 0, if we want to change it into 1, 0 to 1. Current state changed into the next state is 1 means what we need? J is 1, the K may be 0 or 1, right? The third case, so the current state is 1, it will want to change it the next state into 0, 1 to 0. What is the input required? J may be 0 or 1, K is 1. The second, then the last one. The current state is 1 and final, the next state also we want 1, 1 to 1. There is no change means the input what we need? J is 0, 1, the K is 0, right? So this is the input required for these 4 different combination of current state and next state. From 0 to 0 mean what we need? The J is 0, K may be 0 or 1. 0 to 1, if you want to change the current state to next state 0, 1 means J is 1, K may be 0 or 1. From 1 to 0, 0, 1, 1. From 1 to 1, 0, 1, 0. Right. So here the state diagram is available. Here the excitation table for JK flip-flop is available. Now we need to design the excitation table for synchronous counter, 3-bit synchronous counter, right. So what is that, how to find the state diagram? So this is the current position 0 0 0, that is changed to 0 0 1, right. So there are 3 flip flop, we can take it as this is QA, QC, QB, QA. This is QC, QA, QB, QC, like that. There are 3 flip flop, we can name it as ABC. So this is C, B, A, right. See how it is changed. It is changed from 0 0 to 0 0 1. Then it is changed to 0 1 0. So from 0 0 0 to 0 0 1 means what is the input required from this excitation table we need to find. For example, see this 0 is changed to 0. There is no change. This is the flip flop C, B and A. Similarly here the next state QC plus 1, QB plus 1, QA plus 1. See this, the first C flip flop there is no change, right. C 0, both are 0. Both are 0 mean what we need? J is 0, K may be 0 or 1. Similarly the second flip flop B, both are 0, current state and next state. So same thing, J is 0, K is 0 or 1. But the third flip flop A is 0, now it is changed to 1, right. Current state is 0, now changed to 1. So what is the what is the input required for changing from 0 to 1? Is 0 to 1. So the J is 1, K may be 0 or 1, right. Similarly we need to identify, we will go for one more state 0 0 1, right. Now it is changed to 0 1 0. This is the flip flop C. C is from 0 to 0, there is no change, right. What we need? J is 0, K may be 0 or 1. Then second flip flop B changed from 0 to 1, right. If you want to from 0 to 1, what is the input required? J is 1, K may be 0 or 1, right. Similarly the third flip flop A is 1, is now changed to 0, right. Current state is 1, next state is 0. Current state is 1, next state is 0 mean what is the input required? J may be 0 or 1, K is 1, right. Like that we can identify the all different 8 stages. Step by step we need to identify for changing from 0 to 0 or 0 to 1 or 1 to 0, what is the value of J and K for 3 flip flop, right. JA, JB, JC. Similarly KA, KB, KC. We need to identify what is the input to the JK flip flop. That is nothing but excitation table of the synchronous counter. This is excitation table of the JK flip flop, right. Now we will see the excitation table of the synchronous counter, right. This is the present state, what is available in the state diagram 0 0 0, 0 0 1, 0 1 0, nothing but 8-bit combination of binary number. Now this 0 0 0 is changed to 0 0 1, that is this state. From this is the current state, this is the next state. This 0 0 0 is changed to 0 0 1. Again 0 0 1 is changed to 0 1 0. Then it is changed to 0 1 1, right. So this is what is available in the state diagram. This is changed to next state, right. It is from the arrow mark we can easily identify. From 0 1 0 it is changed to 0 1 1, 0 1 0 changed to 0 1 1, right. Finally the 1 1 1 is changed to 0 0. Again 0 0 will change into 0 0 1, like that it will change. Say this is the present state. This simply you can write it as, that is nothing but combination of 8-bit binary number. This is second state. You can see this is 0 0 0. So the next number 0 0 1 is coming here, right, because 0 0 is changed to 0 0 1. Then third number is coming here, the second number, second combination, right. So like that this is the next state. I will explain with the state diagram, right. So present state is this state 0 0 0 0 1 0 1 0, like that. What is the next state? From 0 0 the next state is 0 0 1. For 0 0 1 the next state is 0 1 0. For 0 1 0 next state is 0 1 1, right. So that one position is changing. So based on that we wrote the excitation table for the synchronous counter, right. So this is the present state what is available, this is the next state. So for this we need to identify what is the value of JC KC, the first flip flop, JB KB second flip flop, JA KA the third flip flop, right, CBA, right. First we will see this QC is 0, QC plus 1 also 0, right, both are 0 means what is the input? The J is 0, the K may be 1 or 0, that is indicated by X, right. Now we'll see the excitation table. See, both are 0 means J is 0, K may be 0 or 1, right. So this table is now implemented in the excitation table of the synchronous counter. Then QB is 0, QP plus 1 also 0, then same thing, so here 0x, here also 0x, right. The J is 0, K may be 0 or 1, that is indicated by X. The third, 0 and 1, current state is 0, next state is 1, changed from 0 to 1 mean what is the input needed? J is 1, K may be 0 or 1, X, right. Similarly, next 0 to 0, same thing, 0x, 0 to 1, what we need? 1x, then 1 to 0, x1, right. So all what we discussed in the excitation of the JK flip flop, all are implemented. We need to see what is the current state, what is the next state, what is the input required. Like that we need to write all the columns for C flip flop, B flip flop as well as A flip flop, right. I think we are able to understand. From excitation table we are executing. I already explained one column, one example. 0 to 0 means the J and K will be 0 and X. 0 to 0 mean again 0x. Suppose the current state is 0, next state is 1. We want to change 0 means the JK input will be J is 1 and K is 1 or 0, that is indicated by X. Similarly, we can write all the inputs from the excitation table. Right. After implementing this, after completing this excitation table, we need to find the expression for JC, KC, JB, KB, JA and KA from this value by using the K-map reduction technique, right. So there are 8 expression we need to find: JC, KC, JB, KB, JA and KA, right. Now we'll go to the reduction of K-map. So first we will see for JC. So 3 variable K-map: QC, QB, QA. These are all the 3 inputs, right. Current state. From current state only we are going to find the expression for JC, right. So from the tabular column, this marking are given, the cross mark are 1, right. This K-map technique you already know. So we can combine these two cells, so that what we got? QB, QA, right. So this 0 and 1 is cancelled, only we have 1, 1. 1, 1 means QB, QA. JC equal to QB, QA. Similarly for KC, the input is QC, QB, QA. From the tabular column the marking are given, so we can combine these two. Same thing, what is available here? Same thing, 1, 1. 1, 1 means KB, KA, right. So the JC value is QB and QA. KC value also QB, QA. So we need to implement this while designing the synchronous counter, right. Now we'll go to the JB. For JB, right, from the tabular column this marking are given. These two are 1, these 4s are cross mark, right. So we can combine these 4. While combining these 4, what will happen? These 2 are cancelled. Only we need to verify this second column and third column. In that QB, QB bar both are cancelled. Only we have QA, right. Only the QA is available. QB and QB bar got cancelled. So the JB is nothing but QA. Now we'll go to the KB value. So the KB value, from the tabular column it is marked that 4 cross mark available and 2 ones are there. So we can combine these two cells. If we combine these two cells, these two are cancelled. QC bar and QC cancel. We need to repair only this second column and third column. In that QB and QB bar cancel, only we have QA, right. So JB also QA, KB also QA, right. Now we'll go to the JA. From the tabular column, while marking the JA, what we got? These two cells are 1, these 4 cells are cross mark and these 2 cells are 1, right. So we can combine all 8 cells, all 8 cells are combined. This is called a don't care condition. While grouping we can take the don't care condition, right. So if you take all these 8 cells, these are all cancelled, everything cancelled, only we have JA equal to 1, right. The input to the A flip flop, J flip flop, the A type is 1. Now we'll go to the KA. What is the input for KA? So for KA, from the tabular column it is marked as these 2 are cross mark, don't care condition, these 4 are 1 and last column also don't care condition. So here also we can group all 4 cells, all 8 cells, right? So that what we got, Ka equal to 1, right? Now we got the value of JC, KC, JB, KB, JA and KA, right? JC and KC is nothing but QB, QA, right? JB and KB is nothing but QA. JA and KA is 1, right? So based on that, we need to design the 3-bit up counter, right? So we already discussed that there are 3 flip-flops are required, A, B, C, 3 flip-flop of JK type, JK flip-flop, right? So this is the first flip-flop, JA, KA, JB, KB, JC, KC, right? 3 flip-flops are available. It's a clock pulse. The clock pulse is given to all 3 flip-flop. So this is the output, QA, QA bar, QB, QB bar, QC, QC bar, right? We need to give the input now. What is the input? JA and KA. See this KA, KA and JA is 1. So 1 is given for both JA and KA. What is the input for JB and KB? That is QA. So here the QA is available directly connected to JB and tapping is taken, that is connected to KB also, right? So the JB and KB value is QA, right? What about this JC? JC is nothing but JC and KC, both are QA and QB, right? We need to multiply QA and QB, so that we are using one AND gate. So this is KB, this is KA. So both are connected. Due to AND gate, it will multiply QA and QB. So output of this AND gate is given to JC as well as KC, right? So all 6 inputs are given. JA and KA is 1. Then JB and KB is QA. JC and KC is QA into QB, right? Now we design the 3-bit up counter, so that it will generate the 3-bit up counter, that is from 000 to 111 in a order, right? So in this video we discuss about the design of synchronous 3-bit up counter. Thank you for listening.